In this video, we're going to introduce Clifford algebras, also called geometric algebras, for understanding spinors. So far in this series, we've looked at spinors in 3 dimensions, called Pauli spinors, and spinors in 4-dimensional space-time, called Weyl spinors. We came across these Pauli spinors and Weyl spinors almost by accident, by rewriting 3D and 4D vectors as 2x2 matrices, and finding that we could factor them into a pair of spinors. Clifford algebras are useful because they stop making spinors look like accidents. Clifford algebras give us a consistent recipe for building spinors in any dimension, like 3, 4, 7, or 20 dimensions. This recipe says that spinors are members of minimal left ideals in Clifford algebras. This recipe probably doesn't make much sense now, but it should make sense over the course of the next few videos. Clifford algebras also unite many types of mathematical objects together. In physics, we deal with various objects like scalars, vectors, bivectors, linear maps, and spinors. All of these objects live together side by side in Clifford algebras. Doing physics with Clifford algebras feels a bit like doing physics with the batteries included. Oftentimes, everything we need to solve a problem in physics already lives inside a Clifford algebra, and we don't need to invent any new mathematical objects to solve the problem. For example, Clifford algebras allow us to unite the 4 Maxwell equations of electricity and magnetism together into a single equation. The YouTuber Suji Lakmo has some fantastic introduction videos for Clifford algebras. And if you're looking for some more advanced videos on Clifford algebras, you can look at the Bivector YouTube channel. For Clifford algebra content on spinors specifically, I'll be referring to this thesis by Crystal and Mackenzie in later videos. I've linked all of these sources in the description. So what exactly are Clifford algebras? They can be thought of as a generalization of the complex numbers, quaternions, and the sigma matrices. All of these algebraic systems involve symbols that square to either -1 or +1, and also involve symbols where swapping the order of multiplication gives us a negative sign. This is also called the anti-commutative property. Loosely speaking, Clifford algebras are algebraic structures where we can square symbols to +1 or -1, and also swap their order to get a negative sign. A good first step for learning Clifford algebras is to begin by understanding Grassmann algebras, also called exterior algebras. I realize I'm throwing a lot of names out right now, but Grassmann algebras can be thought of as a stepping stone to learning Clifford algebras, so we're going to start with learning Grassmann algebras. The key idea in Grassmann algebras is the wedge product. If we have a vector u and another vector v, their wedge product, u wedge v, is a plane segment formed by u and v, with an orientation that follows the arrows. If we swap the order of these vectors and look at v wedge u, we get the same plane segment but with the opposite orientation. These oriented plane segments are called bivectors. These bivectors are a useful way for representing rotations and angular momentum. In introductory physics classes, angular momentum is usually represented using a vector, which you get by using the awkward right-hand rule, where you curl the fingers of your right hand in the direction of the rotation and stick your thumb out in the direction of the angular momentum vector. Not only is this awkward, but it can lead to strange geometric results. For example, if we reflect a rotating object in a mirror, the angular momentum vector points in the opposite direction. This is a very strange behavior for a vector and indicates we might be doing something wrong. However, when we represent rotations and angular momentum using bivectors instead, the direction of rotation is immediately obvious, and when we reflect the rotation in a mirror, the bivector changes in a predictable way, reversing the orientation in a way that makes sense. When we have a vector u, its opposite, minus u, is a parallel vector of the same length, but pointing in the opposite direction. When we add u and negative u together, we get 0. Similarly, when we have a bivector u wedge v, its opposite, v wedge u, is a bivector of the same size, but oriented in the opposite direction. When we add u wedge v and v wedge u together, we get 0. For this reason, we can also write v wedge u as negative u wedge v, because it's the same bivector as u wedge v, but with the opposite orientation. This gives us our first important property of the wedge product. When we swap the order of the vectors in the wedge product, we get a negative sign in front. This means that the wedge product is anti-commutative. When it comes to vectors, a vector's magnitude is equal to the length of its arrow. If a vector has length 0, we call it the 0 vector. For bivectors, a bivector's magnitude is equal to the area of its plane segment. If a bivector has 0 area, we call it the 0 bivector. Notice that if we take the wedge product of two vectors that are parallel, we end up with an area of 0, so we get the 0 bivector. In particular, the wedge product of a vector with itself always gives 0. When we have the wedge product used over a sum of vectors, we can distribute the wedge product over the sum, similar to the way we distribute multiplication over brackets in high school algebra. This has an easy visual interpretation. If we add u1 and u2, and then take the wedge product with v, this is the same thing as taking u1 wedge v and u2 wedge v and adding them together into a single oriented plane. This gives us the distributive properties of the wedge product. Also, when we multiply u wedge v by a scalar, like 3, we can either multiply the u by 3 or multiply the v by 3. Mathematically, the results are the same. Now, these results might look different to you visually, however, as long as the areas of the two plane segments are the same and the orientations are the same, the bivectors are considered equal. It doesn't matter if we draw the areas as squares, rectangles, parallelograms, circles, or some other shape. And the angle or rotation of the shape also doesn't matter. For example, any bivector drawn as a parallelogram can be redrawn as a rectangle. The portion of the wedge product involving parallel vectors goes to 0, so we only need the orthogonal portion of the vectors. Also, the property of the wedge product being anti-commutative and the property of a vector wedged with itself equaling 0 are actually equivalent properties and can be derived from each other. If we take the anti-commutative property and set v equals u, we get something that equals the negative of itself, which must be 0. So that proves the equivalence in one direction. If we instead start with this wedge product of a sum, u plus v with itself, and assume anything wedged with itself is 0, we can distribute to get 4 terms, 2 of which go to 0. And we're left with the anti-commutative property. This shows the equivalence in the other direction. Now, we've talked about the abstract properties of bivectors, but I'd also like to talk about bivector components. Let's say we're working in 2D space with basis vectors ex and ey, and we're looking at the bivector u wedge v. What are this bivector's components? We can write u and v as linear combinations of the basis vectors, then distribute over the wedge product to get 4 terms, first, outer, inner, last. The ex wedge ex and ey wedge ey terms go to 0, and we can rewrite ey wedge ex as negative ex wedge ey, using the anti-commutivity of the wedge product. So we find that u wedge v has only one component with the basis bivector ex wedge ey, and the component is ux vy minus uy vx. which is the formula for the area of a parallelogram using vector components. There is only one basis bivector here because in the xy plane, there is only one possible pair of axes. In 3D space, the formula for u wedge v has three components, because there are three possible pairs of axes, yz, zx, and xy. As an exercise, you can try proving that these are the components. These end up being the same components that result from the cross product of u and v. If we continue using the wedge product, we can build higher dimensional multivectors, like trivectors, quad vectors, and so on. However, we can't keep going up forever. In 3 dimensions, for example, the trivector is the highest we can go. If we include an extra wedge product, the result will always go to 0, because we'll always have a vector wedged with itself somewhere. Also, take note that in 3 dimensions, there is only one trivector, possibly with a scaling constant in front, since we can always swap the basis vectors into the xyz order by introducing minus signs as needed. In space with a given dimension, we can count the number of basis multivectors of each type just by counting the number of possible basis vector combinations. As a result, the multivectors in a given Grassmann algebra form a sort of diamond shape, with low-grade multivectors at the bottom and high-grade multivectors at the top. Every multivector has exactly 2 possible orientations, given by a plus or a minus sign. We reverse the orientation of a vector just by flipping the arrow's direction. We can build a bivector using a set of vectors, all oriented so that the tip of one touches the tail of the next, forming the boundary of a plane segment. The orientation of this bivector just follows the orientation of the vectors along the boundary. We can reverse the orientation of the bivector, introducing a negative sign, just by reversing the orientation of the vectors along the boundary. This logic applies for higher dimensions as well. We can build a trivector using a set of bivectors that form the faces of a cube. The rule is, each bivector must be oriented opposite to its neighbors, wherever they share an edge. If we want to reverse the orientation of a trivector, we just reverse the orientations of all its bivector faces. The approach of using the boundary to define the orientation of a multivector applies for multivectors of all dimensions. So that's Grassmann algebras, which are algebraic structures over vector spaces that use the wedge product to build multivectors. Now, what's a Clifford algebra? Loosely speaking, it's an algebra where symbols square to either +1 or -1, and flipping the order of symbols introduces a negative sign, similar to what we saw with Grassmann algebras. This multiplication rule is called the Clifford product, or geometric product, which is denoted by writing symbols next to each other like this. We'll soon see that this leads us to the complex numbers, the quaternions, the sigma matrices, and their generalizations. Instead of starting with a formal definition of Clifford algebras, I'm going to go through a few examples, and then I'll give a definition at the end. So let's look at some examples of Clifford algebras, which are algebras with symbols that square to +1 or -1. Let's say we have a symbol I that squares to -1. One way to approach this is to interpret this as a matrix problem, saying that the number 1 is actually the identity matrix, and the symbol I is actually a matrix like this that squares to the negative identity. The expression A plus IB would then give you a matrix like this. Another way to approach this is to simply treat I as its own symbol, with I squared equals -1 as the definition. This is the more traditional approach, and it's how we normally define complex numbers. What we have here is the Clifford algebra CL01, because we have 0 symbols that square to +1 and a single symbol that squares to -1. So the complex numbers, also called CL01, are a first example of a Clifford algebra. So we have two options for looking at Clifford algebras. We can either look at them using matrices, or we can look at them using abstract symbols. Now, we normally take the second approach of abstract symbols as the more pure or correct definition of the complex numbers, and we prefer it over the matrix approach. The reason is there are an infinite number of matrices of all different sizes that square to the negative identity matrix. We say that these are all matrix representations of the abstract symbol I. But we don't actually need any of these matrix representations to do math with complex numbers. It's often simpler to just take the symbol I as its own object and forget about matrices. As an exercise, you can try multiplying the expression A plus IB times C plus ID in both matrix form and symbolic form, and show that they give equivalent results. Here's another example of a Clifford algebra. Let's say that we have a symbol J which squares to +1. Again, we can interpret this as a matrix problem, saying 1 is the identity matrix, and J is a matrix like this that squares to the identity. So the expression A plus JB would correspond to this matrix here. But once again, there are an infinite number of matrices of all sizes that square to the identity. A simpler approach is to just treat J as its own symbol with J squared equals +1 as the definition. This is the Clifford algebra CL10 because it has a single symbol that squares to +1 and 0 symbols that square to -1. This is also called the split complex numbers. Here's another example. We have 3 symbols, sigma x, sigma y, and sigma z, that all square to +1. But since we now have more than one symbol, we now also need to decide how these symbols will multiply with each other. Let's take some inspiration from Grassmann Algebras. Let's say that when we multiply 2 of these Clifford algebra symbols together, we can flip their order if we include a minus sign. If we approach this as a matrix problem, we get the sigma matrices, or Pauli matrices, that we spent a lot of time talking about in videos 6 to 10. But the Clifford algebra style approach is to forget about the matrices and just treat these 3 sigmas as their own symbols that square to +1 and anti-commute with each other. Actually, if you were to go back and watch video number 6, which covers sigma matrices in detail, you'll notice that almost everything in the video can be figured out without writing down any matrices, and just using these squaring and anti-commutative properties of the sigmas. Again, the sigmas only approach is seen as simpler because we can get all the same results without worrying about matrices. This gives us the Clifford algebra CL30 because we have 3 symbols that square to +1 and 0 symbols that square to -1. And the 3 symbols also anti-commute with each other. This is also called the algebra of physical space. Pairs of different sigmas give us the bivectors in CL30. And it turns out these are completely equivalent to the quaternion imaginary units ij, k. The reasons ij and k anti-commute with each other is rooted in the fact that the sigma pair bivectors also anti-commute with each other. We say that the quaternions are the even grade subalgebra of CL30 because they only involve the grade 0 scalar and the grade 2 bivectors. Here is one final example with 4 symbols: gamma 0, gamma 1, gamma 2, and gamma 3. Gamma 0 squares to +1, and the other 3 gammas square to -1, and all the gammas anti-commute with each other. Treating this as a matrix problem, we can get these matrices, which are called the Dirac matrices or gamma matrices. These will pop up if you've ever studied the Dirac equation for particle physics or quantum field theory. And again, there are multiple solutions. This set of matrices is called the chiral basis or Weyl basis. There's also this alternative solution called the mass basis or Dirac basis. But as usual, I'm going to say it's better to just treat the gammas as their own symbols that obey these squaring and anti-commutative properties, and take those as the definition. This gives us the Clifford algebra CL13 because we have one symbol that squares to +1 and three symbols that square to -1. This is also called the space-time algebra. Suji Lakmo has a great video showing how this can be used to formulate special relativity, linked in the description. So generally speaking, we say that the Clifford algebra CLPQ is an algebra with P symbols that square to +1 and Q symbols that square to -1. And the symbols all anti-commute with each other. Sometimes if Q equals 0 and there are no symbols that square to -1, we can omit the Q in our notation and just write CLP for a Clifford algebra with P symbols that square to +1 and anti-commute. I should mention that this anti-commutation relation is sometimes written like this, with curly braces and the dot product, or metric. If the two symbols are different, these two terms in the sum cancel and we get 0, since the dot product of orthogonal vectors is 0. If the two symbols are the same, we get twice the vector's squared length. As a quick aside, sometimes in Clifford algebras, we also include symbols that square to 0. If we have a symbol epsilon that squares to 0, we can again interpret this as a matrix problem, where 0 is the zero matrix and epsilon is a matrix that squares to 0, like this. But it's more common to treat epsilon as its own symbol, with epsilon squared equals 0 as the definition. These are called the dual numbers. In Clifford algebra notation, we call this CL001, where the first two numbers tell us how many symbols square to +1 and -1, and the third number tells us how many symbols square to 0. These won't come up very often in this video series, but it's useful to know about. So let's compare the wedge product from Grassmann Algebras to the Clifford product in Clifford Algebras. Now, with Grassmann Algebras, I was often talking about vectors. In Clifford Algebras, I was loosely talking about symbols. But we're going to interpret these symbols as basis vectors in Clifford Algebras. For example, with the sigma matrices CL30, we can think of the three symbols as forming a 3D orthonormal basis. This is how we've been treating the sigma matrices in previous videos. With Grassmann algebras, the wedge product of a vector with itself always gives 0, because the resulting plane segment has an area of 0. With Clifford algebras, taking the Clifford product of a vector with itself gives that vector's squared magnitude. Unit vectors in our orthonormal basis square to +1 or -1 because they have a length of 1. Likewise, a vector of length 5 will square to ± or -25. If you're confused about why a vector would square to -1, this ends up being useful in special relativity when we need to tell the difference between time-like vectors and space-like vectors. With Grassmann algebras, anytime we have a wedge product of two vectors, we can always flip their order if we include a negative sign, which is the anti-commutative property. For Clifford algebras, the anti-commutative property applies only for orthogonal vectors. For the sigmas, sigma x, sigma y, and sigma z are all orthogonal, so they all anti-commute with each other. But a given sigma will not anti-commute with an arbitrary vector v, which is not orthogonal to it. Let's look at the Clifford product of two vectors in CL20, where the EX and EY basis vectors both square to +1. We can write vectors u and v in terms of this basis. We can then write the Clifford product, u times v, using distributive properties. First out, inner last, and get 4 terms. The terms with EX squared and EY squared both go to +1, so we get a sum of scalars. Since EX and EY are orthogonal, we can flip EY times EX to get negative EX times EY, using anti-commutativity. We can then group these two terms together. So the Clifford product of two vectors is the sum of a scalar and a bivector. The scalar part looks like the dot product of u and v, and the bivector part looks like the wedge product of u and v. So, loosely speaking, the Clifford product can be thought of as a combination of the dot product and the wedge product. When we take the Clifford product of two orthogonal vectors, u and v, the dot product goes to 0, and we're left with just the wedge product. So we get to use the anti-commutativity of the wedge product in this special case. When we take the Clifford product of two parallel vectors, u and v, the wedge product part goes to 0, and we get u dot v, which also equals v dot u due to the commutativity of the dot product. And remember, the dot product of a vector with itself gives that vector's squared length. Before I finish the video, I'm going to go over some more abstract definitions of Grassmann algebras and Clifford algebras that involve tensor algebras and quotients. This is a little more advanced, and you probably don't need to worry about it if you're a beginner with Clifford algebras. I'm just including this section for completeness for those who want to know about it. I've already talked about the tensor product in video number 8. As a basic review, the tensor product is like an abstract generalization of the outer product of a column vector and a row vector. It obeys distributive properties over addition, just like array multiplication. And distributivity works in both directions. And when multiplying by a scalar, we can either give the scalar to the left-hand side or the right-hand side. We can create tensor products of 2, 3, 4, or any number of vectors. Now I'll introduce the tensor algebra. Let's say that we have a two-dimensional vector space V with basis vectors e1 and e2. The tensor algebra of V, denoted T of V, includes scalars, all the vectors in V, all the tensor products of two vectors in V, all the tensor products of three vectors in V, and so on up to infinity. As we increase the number of tensor products, the number of possible terms increases exponentially. Individual vectors live in the vector space V. Vector pairs live in V tensor V, also written V squared. Vector triples live in V tensor V, or V cubed, and so on. Scalars live in the set of scalars S, which is sometimes written as V to the power of 0. In tensor algebras, we can add together arbitrary elements from this infinite collection. So we can write expressions like 2 plus 3e1 minus 5e2 tensor e1 tensor e2. Now let's try modifying our tensor algebra with a special rule. We're going to say that anytime we see a vector tensored with itself, it will go to 0. This leaves scalars unchanged and also leaves individual vectors unchanged. But with tensor products of two vectors, e1 tensor e1 and e2 tensor e2 now get sent to 0. But as we proved earlier, the property of a vector product with itself equaling 0 automatically implies that we can swap the order of a product if we introduce a negative sign. So using this new rule, e1 tensor e2 equals negative e2 tensor e1. For the tensor product of three vectors, it turns out every single term goes to 0, since all terms contain at least one pair of identical basis vectors. This applies for any larger tensor products as well. So using this new rule, we've eliminated a huge number of infinite tensor products, and we're left with only 4. What we're left with is exactly the rules for the Grassmann algebra. So abstractly, the Grassmann algebra is what we get when we start with the tensor algebra and apply the special rule that any vector tensored with itself goes to 0. More formally, we say that the Grassmann algebra is what we get when we take the quotient of the tensor algebra by the ideal generated by V tensor V. We can start over and do this again, but with a slightly modified rule, where we take any vector tensored with itself, and instead of setting it to 0, we set it to that vector's squared length. Using this rule, scalars and individual vectors are unaffected. E1 tensor E1 and E2 tensor E2 are now equal to the scalar 1. This property also results in the anti-commutative property if two vectors are orthogonal. This is because orthogonal vectors obey a Pythagoras formula, which allows us to cancel the terms from both sides of this equation. And so because E1 and E2 are orthogonal, we get that E2 tensor E1 equals negative E1 tensor E2. For the terms with 3 vectors in the product, any identical vectors get sent to the scalar +1, so we're left with just individual vectors, which we already have in our algebra. In fact, any more complicated combination of vectors will always give us either scalars, vectors, or bivectors. So again, we've removed all the higher infinite number of terms, and we're left with only 4 terms. This is exactly the Clifford algebra CL20, where vectors square to their squared magnitudes, and orthogonal vectors anti-commute. So abstractly, the Clifford algebra is what we get when we start with the tensor algebra and apply the special rule that any vector tensored with itself goes to its squared length. More formally, we say that the Clifford algebra is what we get when we take the quotient of the tensor algebra by the ideal generated by V tensor V minus the squared magnitude of V. You might also see this magnitude formula written with a G. This is called the metric tensor, and it's just a function that gives vector lengths. So to conclude, a Clifford algebra, also called a geometric algebra, is what we get when we take a vector space and allow multiplication between vectors using the Clifford product, also called the geometric product. The Clifford product of a vector with itself gives that vector's squared magnitude, and the Clifford product of 2 orthogonal vectors is anti-commutative, so we can swap the order if we include a negative sign. In the next video, we're going to see how we can use Clifford algebras to build spin groups in any dimension. These are groups that double cover the rotation group in a given dimension, and do rotations and Lorentz boosts using double-sided transformations.